Right now, as you watch this video, the James Webb Space Telescope is analyzing the atmospheres of distant worlds, searching for the chemical fingerprints that could prove we're not alone in the universe. In the past 2 years, Webb has revolutionized our ability to study exoplanet atmospheres with unprecedented precision, bringing us closer than ever to answering humanity's oldest question: is there life beyond Earth? Today, we're diving into the cutting-edge science of biosignature detection, exploring how astronomers are learning to read the atmospheric chemistry of alien worlds, and examining the real discoveries that are reshaping our understanding of life in the cosmos. Subscribe now, because the hunt for extraterrestrial life has never been more exciting or more scientifically rigorous. The James Webb Space Telescope has fundamentally changed how we study distant worlds. Unlike previous space telescopes that could barely detect the existence of exoplanets, Webb can analyze the chemical composition of their atmospheres in extraordinary detail. In 2022, Webb made headlines with its first exoplanet atmospheric analysis of WASP-96b, a gas giant 1,150 light-years away. The telescope detected water vapor, clouds, and atmospheric haze with a precision that would have been impossible just a few years ago. But this was just the beginning of Webb's atmospheric revolution. The telescope works by observing planetary transits, when an exoplanet passes in front of its host star from our perspective. During these cosmic eclipses, starlight filters through the planet's atmosphere, and different molecules absorb specific wavelengths of infrared light. Webb's instruments can detect these tiny absorption signatures, creating detailed atmospheric profiles of worlds dozens or hundreds of light-years away. This technique, called transmission spectroscopy, is like cosmic forensics. Scientists can identify water vapor, carbon dioxide, methane, and potentially even more complex molecules by studying how they interact with starlight. The precision is staggering. Webb can detect atmospheric features that represent changes of less than 0.01% in stellar brightness. The technological achievement cannot be overstated. Webb's 6.5-meter primary mirror collects nearly 7 times more light than Hubble, while its infrared instruments operate at temperatures just degrees above absolute zero to eliminate thermal noise. The result is sensitivity to molecular signatures that were completely invisible to previous generations of telescopes. When astrobiologists talk about finding life on other worlds, they're not looking for little green aliens or radio signals. They are hunting for biosignatures, chemical evidence of biological processes in planetary atmospheres. On Earth, life has dramatically altered our atmosphere's composition. Oxygen makes up 21% of our air, but this gas is so reactive that it would disappear within a few million years without living organisms constantly replenishing it through photosynthesis. The presence of oxygen alongside gases like methane creates what scientists call chemical disequilibrium, combinations of molecules that shouldn't coexist without active biological processes. Scientists have identified several potential biosignature gases that could indicate life on distant worlds. Oxygen and ozone suggest photosynthetic organisms. Methane could indicate biological metabolism. Phosphine, a molecule that on Earth is only produced by living organisms, will be an unambiguous sign of biological activity. But detecting these signatures requires careful analysis. Scientists must rule out geological processes that might produce similar atmospheric chemistry. Volcanic activity can release various gases. Lightning can create complex chemical reactions, and photochemical processes driven by stellar radiation can mimic some biosignatures. The challenge is enormous. Imagine trying to determine whether a distant city has life by analyzing the light from its street lamps. That's essentially what astronomers are attempting when they search for biosignatures in exoplanet atmospheres across interstellar distances. Webb has already made several groundbreaking discoveries that are advancing our understanding of atmospheric chemistry on other worlds. K2-18b, a sub-Neptune 124 light-years away, became one of Webb's most significant early targets for atmospheric analysis. In 2023, Webb detected water vapor and clouds in K2-18b's atmosphere, confirming that this world orbits within its star's habitable zone where liquid water could potentially exist. More intriguingly, the telescope also detected methane and carbon dioxide in ratios that warrant further investigation for potential biological origins. The presence of methane alongside water vapor is particularly interesting because these molecules can coexist in atmospheres where biological processes might be active. However, scientists emphasize that non-biological explanations remain possible, and additional observations are needed to determine the true nature of K2-18b's atmospheric chemistry. Webb has also studied the TRAPPIST-1 system, 7 Earth-sized planets orbiting a red dwarf star just 40 light-years away. Initial observations of TRAPPIST-1b revealed it likely has little to no atmosphere due to intense stellar radiation. But other planets in the system remain targets for atmospheric analysis that could reveal more hospitable conditions. The telescope's observations of hot Jupiters have revealed atmospheric compositions that challenge planetary formation theories. WASP-39b showed unexpected levels of sulfur dioxide, water vapor, and carbon monoxide, demonstrating that atmospheric chemistry can be far more complex than simple models predicted. Searching for biosignatures presents enormous technical and scientific challenges. The signals are incredibly weak. Atmospheric absorption features might represent changes of just 0.001% in stellar brightness. Distinguishing these tiny signals from instrumental noise, stellar variability, and atmospheric interference requires unprecedented precision. Weather on exoplanets adds another layer of complexity. Clouds can block or scatter light in ways that alter atmospheric signatures, potentially masking biosignatures or creating false positives. Seasonal variations in atmospheric chemistry mean that single observations might not provide a complete picture of a planet's atmospheric state. Stellar activity creates additional complications. Many exoplanets orbit red dwarf stars that produce frequent flares and variable radiation levels. These stellar changes can alter planetary atmospheric chemistry and create spectral signatures that might be mistaken for biological activity. The interpretation of atmospheric data requires sophisticated computer models that account for atmospheric physics, photochemistry, and potential biological processes. Scientists must consider multiple scenarios for how observed atmospheric compositions might arise, carefully weighing the probability of biological versus non-biological explanations. Contamination from Earth's atmosphere presents another challenge for ground-based observations. Water vapor, carbon dioxide, and other molecules in our atmosphere can interfere with exoplanet atmospheric signals. Space-based telescopes like Webb avoid this problem, but have limited observation time and must prioritize targets carefully. Webb's atmospheric observations are revolutionizing our understanding of planetary habitability. The traditional concept of a habitable zone, the orbital distance where liquid water can exist on a planet's surface, is proving to be more complex than astronomers initially thought. K2-18b orbits well within its star's habitable zone, but Webb's observations suggest it's likely a Hycean world, a hydrogen-rich planet with a global ocean beneath a thick atmosphere. This type of world wasn't included in traditional habitability models, but might be more common and potentially more habitable than Earth-like planets. The telescope's infrared capabilities allow it to study atmospheric chemistry in ways that reveal whether planets can maintain stable climates over geological timescales. Greenhouse gases, cloud formation, and atmospheric circulation patterns all influence whether a world can sustain conditions suitable for life. Webb has also revealed that many planets in habitable zones have retained thick hydrogen atmospheres from their formation. Previous theories suggested that hydrogen would escape to space, but observations show these atmospheres can persist and might actually enhance habitability by providing greenhouse warming and pressure that stabilizes liquid water. The diversity of atmospheric compositions discovered by Webb suggests that habitable worlds might be more common, but also more varied than Earth-like planets. Instead of looking only for atmospheric twins of our planet, astronomers are learning to recognize habitability in atmospheric compositions that differ dramatically from Earth's. Red dwarf stars, which make up 75% of all stars in our galaxy, were long considered poor hosts for habitable planets due to their tendency to produce violent stellar flares. Webb's observations are challenging this assumption by revealing that some red dwarf systems might actually be excellent places to look for life. The TRAPPIST. One system exemplifies the potential of red dwarf planets. While TRAPPIST-1b appears to have lost its atmosphere, other planets in the system might have retained their atmospheres and could potentially harbor habitable conditions. Webb's ongoing observations will reveal whether these worlds have the atmospheric compositions needed for habitability. Red dwarf stars offer several advantages for life. They burn hydrogen so efficiently that they can maintain stable energy output for trillions of years, far longer than sun-like stars. This extended timescale provides enormous opportunities for biological evolution to develop complexity over geological time periods that dwarf Earth's biological history. The close orbital distances required for planets to receive adequate energy from red dwarf stars create tidal locking, where one hemisphere always faces the star. Webb's atmospheric observations can reveal whether tidally locked planets can maintain global atmospheric circulation that distributes heat and prevents atmospheric collapse. Recent Webb observations suggest that some red dwarf planets might have atmospheric compositions that provide natural protection from stellar flares. Thick hydrogen atmospheres could absorb harmful radiation while maintaining surface conditions suitable for liquid water and potentially life. In 2020, astronomers announced the detection of phosphine in Venus's atmosphere, creating worldwide excitement about the possibility of life in our solar system's most inhospitable planet. The discovery sparked intense scientific debate that illustrates both the promise and challenges of biosignature detection. Phosphine is considered a potential biosignature because, on Earth, it's primarily produced by anaerobic bacteria in oxygen-free environments. The molecule is highly reactive and breaks down quickly in oxidizing atmospheres, so its presence requires continuous production to maintain detectable concentrations. Follow-up observations and reanalysis of the Venus data have yielded conflicting results. Some studies confirm phosphine's presence while others suggest the original detection might have been misinterpreted sulfur dioxide signatures. The controversy highlights the difficulty of definitively identifying biosignatures even in our own solar system. The phosphine debate has driven improvements in atmospheric analysis techniques that benefit Webb's exoplanet observations. Scientists are developing more sophisticated methods for distinguishing between different molecular signatures and ruling out non-biological explanations for unusual atmospheric compositions. Venus's extreme conditions, surface temperatures of 900 degrees Fahrenheit and atmospheric pressures 90 times greater than Earth's, make it an unlikely habitat for life as we know it. But the upper atmosphere, where phosphine was allegedly detected, has more moderate temperatures and pressures that might conceivably support microbial life. Webb's observations are revealing that exoplanet atmospheres exhibit remarkable diversity and complexity. Different atmospheric layers can have distinct chemical compositions, creating stratified environments that might support various types of chemical or biological processes. The telescope's ability to analyze atmospheric structure in 3 dimensions allows scientists to study how gases are distributed vertically through planetary atmospheres. This information provides crucial insights into atmospheric dynamics, weather patterns, and the physical processes that shape planetary environments. Cloud formation and atmospheric circulation patterns influence how biosignatures might be distributed and detected. Webb's observations show that some exoplanets have complex weather systems with regional variations in atmospheric composition that could affect biosignature detection depending on which parts of the planet are observed during transit events. Temperature and pressure profiles derived from Webb's spectroscopic data reveal the physical conditions at different atmospheric levels. These measurements help scientists understand whether planets can maintain the stable environmental conditions needed for complex chemistry or biological processes. The discovery of atmospheric layering on exoplanets has implications for habitability. Different atmospheric zones might provide distinct ecological niches where different types of organisms could potentially thrive, expanding the range of environments that might support life beyond simple surface habitability models. As Webb observes more exoplanets, astronomers are beginning to understand the statistical distribution of atmospheric compositions throughout the galaxy. This data is crucial for estimating how common potentially habitable worlds might be and where to focus future biosignature searches. Early Webb observations suggest that atmospheric retention is more common than previous models predicted. Many planets appear to have maintained substantial atmospheres over billions of years, creating opportunities for complex atmospheric chemistry that might support biological processes. The diversity of observed atmospheric compositions indicates that habitable worlds might exist in forms quite different from Earth. Instead of looking only for atmospheric twins of our planet, scientists are learning to recognize habitability indicators in atmospheric chemistries that operate according to different principles. Statistical analysis of Webb's atmospheric surveys will eventually provide the data needed to estimate the frequency of potentially habitable worlds around different types of stars. This information is essential for planning future missions and understanding humanity's place in a potentially populated galaxy. The accumulating database of exoplanet atmospheric compositions is already influencing theories about planetary formation and evolution. Webb's observations show that atmospheric chemistry can be far more complex and varied than theoretical models initially predicted. Webb represents just the beginning of humanity's capability to study exoplanet atmospheres and search for biosignatures. Several next-generation telescopes currently in development will extend these capabilities even further, potentially providing the sensitivity needed to detect unambiguous signs of extraterrestrial life. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will survey thousands of exoplanets using gravitational microlensing techniques. While not designed primarily for atmospheric analysis, Roman will identify numerous potentially habitable worlds that could become targets for biosignature studies. The proposed Habitable Exoplanet Observatory, HabEx, will be specifically designed to directly image Earth-like exoplanets and analyze their atmospheric compositions. Direct imaging would eliminate many of the complications associated with transit spectroscopy and enable detailed studies of planetary atmospheres and surface conditions. Ground-based telescopes are also advancing rapidly. The Extremely Large Telescope, ELT, with a 39-meter primary mirror, will have the light-gathering power and resolution needed to study exoplanet atmospheres from Earth's surface using adaptive optics to correct for atmospheric interference. Technological developments in infrared detectors, spectrographs, and data analysis techniques continue to improve the sensitivity and precision of atmospheric observations. Future missions will be able to detect weaker biosignature signals and distinguish between biological and non-biological atmospheric chemistry with greater confidence. The hunt for biosignatures represents one of the most challenging and potentially rewarding scientific endeavors in human history. Webb's observations have demonstrated that we now possess the technology to analyze exoplanet atmospheres with the precision needed to potentially detect signs of extraterrestrial life. Current observations focus on the most promising targets, planets in habitable zones around nearby stars where atmospheric signals are strongest and observing conditions are most favorable. Each new atmospheric analysis adds to our understanding of planetary atmospheres and refines techniques for biosignature detection. The search requires patience and rigorous scientific methodology. Biosignature detection will likely require multiple independent observations, careful analysis to rule out non-biological explanations, and peer review by the international scientific community before claims of extraterrestrial life can be confirmed. International collaboration is essential for biosignature research. Space agencies, universities, and research institutions around the world are coordinating observations, sharing data, and developing the theoretical frameworks needed to interpret atmospheric observations of distant worlds. The scientific community maintains appropriate skepticism while pursuing biosignature research with unprecedented technical capabilities. The potential for false positives requires that any biosignature claims undergo rigorous verification before being accepted as evidence of extraterrestrial life. The search for biosignatures through atmospheric analysis represents a new chapter in humanity's exploration of the cosmos. Even if definitive detection of extraterrestrial life remains elusive, the search itself is advancing our understanding of planetary science, atmospheric chemistry, and the conditions needed for habitability. Webb's atmospheric observations are already influencing our understanding of Earth's own atmospheric evolution and the factors that maintain our planet's habitability. Comparative planetology helps scientists understand how rare or common Earth-like conditions might be throughout the galaxy. The technical developments driven by biosignature research have applications beyond astronomy. Advanced spectroscopic techniques, data analysis methods, and atmospheric modeling have potential applications in Earth observation, climate science, and industrial applications. Educational institutions worldwide are incorporating exoplanet science and astrobiology into their curricula, preparing new generations of scientists to continue the search for life beyond Earth using increasingly sophisticated observational techniques and theoretical frameworks. The search for biosignatures also raises important philosophical and ethical questions about humanity's responsibilities as we potentially discover other forms of life in the universe. These discussions are happening now, before definitive discoveries are made. We stand at the threshold of a new era in astronomy where the atmospheric chemistry of distant worlds has become accessible to scientific study. The James Webb Space Telescope has demonstrated that we can analyze the atmospheric compositions of exoplanets with unprecedented precision, bringing us closer than ever to answering whether life exists beyond Earth. The hunt for biosignatures continues with rigorous scientific methodology, advanced technology, and international collaboration. While definitive detection of extraterrestrial life remains elusive, each atmospheric observation adds to our understanding of planetary diversity and the conditions that might support biological processes. Webb's ongoing observations will likely identify atmospheric compositions that warrant further investigation as potential biosignature candidates. The telescope's operational lifetime of at least 20 years ensures that atmospheric studies will continue advancing throughout the next decade. The search for life through atmospheric analysis represents one of humanity's greatest scientific adventures. Whether or not we discover definitive evidence of extraterrestrial life, the journey is advancing our understanding of planets, atmospheres, and the cosmic conditions that might allow biology to flourish throughout the universe. The atmospheric revolution has begun, and every new observation brings us one step closer to answering the fundamental question: are we alone?